A construction company needs to erect a temporary access bridge to a construction site for 1 year in an area of known seismic activity. They must decide what degree of earthquake resistance should be incorporated into the design to minimise total costs associated with seismic design and damages. 40 earthquakes have occurred in the past 50 years. Here is our data that we're going to use to solve this problem. So we've got 50 years of data, and in those 50 years we've had 10 years with no earthquakes, 24 years with small earthquakes, 12 with medium-sized ones, and 4 years with large ones. Now we have different options of how we can strengthen our building to deal with the earthquakes. We could of course do nothing, in which case if there's no earthquake, there's no problem. But if there is a larger earthquake, there is damage to our building that needs to be repaired based on how big the earthquake is. As we do more and more, as we strengthen the building more and more, it's able to cope with larger earthquakes. So $1,000 means that a small earthquake won't be a problem, and a medium earthquake will be a smaller problem than it would have been otherwise. $6,000 will set us up so that we don't have to deal with any earthquake damage at all. Now, of course, we care about how much do we have to pay for the strengthening, plus how much do we have to pay for the actual damage cost. To solve this problem, we start with a decision node. And we have different options of what we can do. So let's first put in the option of not strengthening it at all. So in this case, there are 4 outcomes that are going to give us different results. So we need to look at all of them. The first one is no earthquake. The second one is a small earthquake. The next one is a medium-sized earthquake. And the last one is a large earthquake. So, the probabilities for these happening: a small earthquake, we had 10 in 50 years, so that will give us a probability of 0.2. For a small earthquake, we had 24 in 50 years, so that will give us a probability of 0.48. For the medium size, we had 12, so we'll get 0.24. And for the small earthquake, we had 4, so we've got a probability of 0.08, based on a total set of data of 50 years. Now, for each one of these leaf nodes, what is the total cost we have to deal with? Well, if there's no earthquake and we didn't design for one, we end up with a total cost of 0. If we didn't design for one, but there is a small earthquake, we have to pay repair costs of $3,000. If there's a medium-sized earthquake, we have to pay repair costs of $5,000. And if there's a large earthquake, we have to pay repair costs of $8,000. Next, we're going to look at what happens if we strengthen it a small amount. So in this case, we're going to spend $1,000 on strengthening our structure. So this time, the first 2 options have no cost, so therefore we'll combine them. So none or less than 4, which has a probability, both of these are included, so it's going to be 0.68. The next case is just the medium-sized earthquakes. So it's going to be 4 to 7, which once again has a probability of 0.24. And the large ones, so greater than 7, once again has a probability of 0.08. However, our calculations will be different. This time, we have to realise that we spent $1,000 to make the structure. This time, we have to remember we spent $1,000 to add the strength to the structure. So in this case, no earthquake happens, but we still spend that $1,000. In this case, we spend the $1,000, but we still have to do $3,000 worth of repairs. So that gives us a total of $4,000. And in this case, we still spend the $1,000 and we have to do $7,000 of repairs. So that gives us a total of $8,000. Now we're going to look at what happens if we do some more strengthening. So in this case, we've got $3,000 worth of strengthening. And once again, there are different options that could happen. If it's an earthquake of less than 7 magnitude or no earthquake, we don't pay anything. If it's a large earthquake, then we pay the $4,000. So our two options that we care about are none or less than 7. Probability of this occurring, well, we have 10, 24 and 12 earthquakes in this category, which is 36 out of 50, which gives us 0.92 as our probability. And we still have to worry differently about the large earthquakes. So this is going to be greater than 7, so 0.08. So if we have no earthquake, we've spent $3,000 to fix it, we don't have any repair costs, so total we'll spend $3,000. On the other hand, if we do have an earthquake, we have $4,000 worth of repair costs plus the $3,000 of strengthening, which gives us $7,000. Now our last option is to strengthen it so much that there will be no problem, and that will simply give us a result of paying $6,000 for the strengthening. So that was the cost of $6,000 worth of strengthening. Okay, now we have our decision tree worked out. We need to solve it by working out the expected monetary value for each of these nodes. For this one, we already know the answer. For the chance nodes, we have to calculate it. So what we do is we go 0.2 times 0 plus 0.48 times 3,000 plus 0.24 times 5,000 plus 0.08 times 8,000. Now this happens to equal $3,280. For this branch, we need to have 0.9. For this branch, we need to have 0.68 times 1,000 plus 0.24 times 4,000 plus 0.08 times 8,000, which gives us 2,600. For this one, we have 0.92 times 3,000 plus 0.08 times 7,000, which gives us 3,320. Now what we do is we compare these different answers. Compare this one to this one to this one to this one. These numbers are all costs, and we want to minimize our costs. So out of these 4 answers, the minimum one is 2,600. So this will be our final answer.